Today it's the last lecture of this series, and I'm going to show you how the concepts we have developed in the previous lectures can be applied to the problem of the time-energy uncertainty relation. In fact, in order to do that, we are going to develop some notions on the geometry of quantum states, and these notions will lead us to a derivation of the so-called time-energy uncertainty relation, but which is actually much more general because it applies not only to closed systems but also to open systems. Furthermore, the notions on the geometry of quantum states, geometry of the space of quantum states, will lead us to some geometrical interpretation of the quantum Fisher information. Let me remind you of the main results we have obtained up to now. We showed in the first lecture that the Fisher information was defined by this expression here, or equivalently by this expression here. We have also defined in the second lecture the quantum Fisher information, which is given by the maximum of the Fisher information over all possible measurements made on the probe state. And I remind you that the probe depends on the parameter we want to estimate. It interacts, say, with a dynamical system, and then we measure the probe afterwards. So that's the quantum Fisher information. And with that, we have shown that the lower bound for the precision in the measurement of the parameter x is given by this expression. So this is the quantum Kramer-Rao relation. The standard deviation is bounded below by 1 over square root of the number of repetitions of the experiment times the quantum Fisher information. Now, we have also shown that for pure states that evolve according to an expression like this is a unitary evolution that depends on the parameter to be estimated. That's the state of the probe. The quantum Fisher information is given by a very simple expression where this is just the variance of an operator in the initial state of the system. That's an x-dependent operator. It's like a Heisenberg operator. And this operator is defined in terms of the unitary evolution by this expression, so you can think of it actually as the generator of the unitary evolution. We have also shown that there is another possible expression for the quantum Fisher information, which is useful in some cases, and that's the expression we showed. It depends on the derivative of the probe state with respect to the parameter to be estimated, and it's very easy to show that this is equivalent to that. You just have to use, say, Schrödinger's equation for the psi dx. Now, all of this is valid for unitary evolutions. What about open systems? There we have a problem. There is not such a simple expression for the quantum Fisher information in that case. So what we have developed is an extended space approach. If you have some system S that is in contact with some environment E, this is not a closed system, it's an open system. So in order to calculate a bound, an upper bound for the quantum Fisher information for the system, we extend the space. We consider the full thing. And in fact, the full thing does not have to be necessarily physical. We add to the system S some environment such that the complete evolution is unitary. That's called a purification procedure. And of course, it must satisfy a very important condition, namely that when we trace out the environment, that is the reduced evolution, corresponds to the real evolution of the density matrix of system S. So this is the purification procedure. And then what we have shown is that the quantum Fisher information for the system, which is equal to the maximum over all possible measurements on the system alone, but not on the environment, is bounded above by the maximum of the Fisher information for the whole thing over all possible measurements done on system plus environment. Okay, so we have more freedom to do measurements here, and therefore this maximization usually leads to a value which is larger than this one. And we call this C of Q. So that's the, say, the Fisher information corresponding to the whole thing. In fact, the quantum Fisher information corresponding to the whole thing. And now, since we have a unitary evolution for system plus environment, we can actually calculate this quantum Fisher information for the whole thing in terms of the variance of the generator of this transformation here. Now, the physical meaning of this bound, therefore, is the information obtained about the parameter when S plus E is monitored, is measured. And we are actually interested in the least upper bound. We would like to have a minimization of C of Q over all possible evolutions in S plus E. And of course, this is a difficult problem in general. However, we have shown that in this paper here, that this bound is actually attainable. In other words, there is always a purification such that this quantum Fisher information for the whole thing coincides with the quantum Fisher information for the system. So the challenge then is to find this best purification that would lead to the quantum Fisher information. In general, this is not possible. However, we can still do something fine. We can find some C of Q, which is close enough to the quantum Fisher information of the system, and which allows some analytical understanding of what's going on, as, for instance, the decoherence increases. So if we find this condition here, then that means that monitoring S plus E uses the same information on the parameter as monitoring S plus E alone. So C of Q coincides then with the quantum Fisher information for the system. Okay? Now, we have also shown that in order to undergo this minimization procedure, we can use the fact that if you have a purification of the evolution of a system, then any other purification for the same evolution can be written like this. So this involves a unitary evolution on the environment alone. We don't have to apply this evolution on the system. Now we define in the same way as before some generator of this unitary evolution, and then the problem is now to minimize C of Q over all Hermitian operators HE that act on the environment. Okay, so that's the procedure that we have adopted, and we are going to give other examples of that in this lecture. So enough for the review. So let's go now to this energy-time uncertainty relation, which has a very old history, actually, in the physics of the 20th century. So you see here, this is the original paper of Heisenberg on the uncertainty relations. And maybe you can see here an uncertainty, a commutation relation between energy and time. Okay? So according to Heisenberg, the presence of this time operator would imply the energy-time relation, uncertainty relation, stemming from this commutation relation. Later on, Pauli showed that if you have such a relation, then necessarily the energy of the system is unbounded below, because the time operator would be then a generator of displacements of the energy, and it's unbounded. And some people have actually shown that you can define a time operator in some cases, some specific cases, but they are very special ones. Of course, this was also present in the famous discussion between Niels Bohr and Einstein. This is the box thought experiment, which Einstein used to show that if you release a photon at some time, which can actually be found with as small an uncertainty as you want, the energy of this box will be reduced. And by weighting the box, you can know what was the energy that was taken by the photon. So in this way, you would know the energy of the photon and the time of release with arbitrary precision, which would seem to disprove this. And then Niels Bohr, after maybe a desperate night, showed that general relativity will not allow that, because if you want to measure this box, you have some uncertainty in the measurement. This uncertainty measure the mass of the box. How do you do that? You have a spring here. You should be able to measure some displacement of the box because of this change in the mass. Now, if you measure the mass, that means that you are going to get some displacement. If you get some displacement in the gravitational field, that induces some change in time. And since you have some imprecision in the measurement, this will result in an imprecision in the measurement of time. And by using this argument, Niels Bohr showed that actually that delta E, delta T is recovered. It was not a correct argument after all, because it neglected the fact that the box is actually entangled with the photon that comes out. So by measuring the energy of the box, you change the energy of the photon as well. And therefore you change delta T for the photon. And you can show that if you consider the intrication or entanglement in this case, you satisfy this relation. Okay. Now, later on, in 1945, Mandelstam and Tam had a very important paper where they derived an uncertainty relation for energy in time. And in this case, they had to define what this interval of time meant. And the paper actually has two parts. The first one is more known than the second one, even though the second part is much more precise than the first one, and much more modern, actually, than the first one. So what was their argument, basically? Well, you see, they started from two relations, which is this one, which comes out from the Heisenberg uncertainty relation between some observable of the system, and which is called here clock observable, and the energy of the system. So this product of standard deviations should be larger or equal than this term that depends on the commutator between the operator and the Hamiltonian of the system. One also knows that the derivative of the average of A with respect to time is given by this expression in terms of the commutator. And using these two relations here, so replacing here this commutator by this derivative, we get to this expression here. So now we see that delta E, delta A is larger or equal than this term here. And now we integrate this equation with respect to time and use that the integration of the magnitude of this expression is larger or equal than the magnitude of the integration of this expression. So by using that, we find that delta E, delta T integrated over time is larger or equal than this expression here. This is just the integration of the derivative of the average with respect to time, divided by this delta A bar, and delta A bar is just the time average of delta A over the integration region. So we have delta T here, and therefore delta T here as well. Okay, so just integrate that, and you get that. Now, we now define the time interval delta T as the shortest time for which the average value of A changes by an amount equal to its average standard deviation. Okay? So this is equal to that, so this whole thing is equal to 1, and then you get this expression here. Okay? So the trick was not to define a time operator, they defined a clock observable, and this time lag was defined in terms of the change of this observable. Now, in the same paper, however, they got a much more precise statement, which is very much connected to the modern approach to this. Again, they started from this equation, and now they define A as the projection operator onto the initial state. Okay, so that's the definition of A now for them. Now, this is a projection operator on a pure state, so therefore the square of this operator is equal to itself. You project twice. It's equivalent to the first projection. So the standard deviation of this operator now is given, as usual, by this expression, which can be written like that. Okay? So because of this property, the standard deviation of the projector can be written in terms of the average value of the projector. So now you replace this in this equation. So you have that, divide all the two members by delta A, which is delta P0 in this case. So you get that delta E is larger or equal than this expression here. And now you integrate both sides of this expression from 0 to tau. Now, you use also, again, that the integration of the magnitude of some expression is larger or equal than the magnitude of the integral of the expression. And if you integrate that, you see this is simple to integrate. It's just the derivative of an arc cosine. So you get that delta E times tau, that's the integration of the left-hand side, is equal to h bar r cosine of square root of the average value of p0 at time tau. Now, you see that since p0 is equal to that, the average value of p0 at time tau is just the fidelity between the initial and the final state. It's the projection of the final state on the initial state squared. So that's the expression they derived. In fact, when I write arc cosine here, I'm assuming that the image of arc cosine is defined in this interval between 0 and pi, and this will be the case all over this, throughout this lecture. Now, suppose now the final state is orthogonal to the initial one, then the projection of the final state on the initial state, which is this average value here, is going to be 0. Arc cosine 0 in the interval from 0 to pi is pi over 2. So you get immediately this expression here. Okay? So this is, I'm going to call this the Mandelstam-Thumb uncertainty relation. It's different from the previous one, because the previous one involved an h bar. Okay? And the reason of the difference is that the criterion for distinguishability, say, was different. In that case, you had the average value of A being displaced by a quantity equal to the standard deviation. Here you require the two states to be orthogonal to each other. Okay? So that's the relation they derived in that paper, and that's the energy-time uncertainty relation. In fact, if you look back to the steps leading to this expression here, you see that they also hold if h depends on time. And then if you integrate this with respect to time, instead of having delta E times tau, we now have this integral here. So this is a generalized Mandelstam-Thumb relation for time-dependent Hamiltonian. And you see that this is an implicit bound now for the time needed to reach some fidelity given by this expression between the initial and the final state. Now, later on, that was in 1990, that expression was derived using a geometrical derivation. And the basic argument, which we are going to use here in some minutes, is that this inequality could be derived from the condition that the actual path followed by the state in the space of quantum states should be actually either larger or at least equal to the geodesic connecting the two states. Okay? So you can interpret this energy-time uncertainty relation as a geometric relation, and we are going to see that in detail later on. Now, what we want to do this is to generalize this to non-unitary processes. Now, why is that? Well, we would like, for instance, to calculate the lifetime for decay processes, necessary an open system. And if we do that, the Hamiltonian should not show up, because it's an open system. You know, we cannot define a Hamiltonian in this case in general. Now, there are many motivations for doing this study. First, it is related to the foundations of quantum mechanics, how to interpret this relation. And in fact, there has been a long debate in the literature on that, involving, among others, these people here, related to the interpretation of this relation. Then we might be interested, for instance, in calculating computation times. For instance, the time taken to flip a spin. And that's related to the quantum speed limit, which is very closely related, as we are going to see, to the energy-time uncertainty relation. But of course, in general, the spin should be in contact with some environment, so it's not a closed system. So how can you say something about this quantum speed limit? This is also important for the quantum classical transition. We might be interested in having some general approach to the decoherence time, for instance. And that suggests an approach along that line. Fourth motivation, we might be interested in controlling quantum systems. That means that we have some external agents, and we want to make the quantum system to go through some path in the space of quantum states. The the basic problem, say, is to find the fastest evolution given some initially final states and some restriction on the resources, for instance, the energy, or the general structure of some Hamiltonian you have. So how can you do it in the fastest possible way? And finally, of course, the relation with quantum metrology, which is directly related to these lectures. So let me start then with some notions on the geometry of quantum states. First, some general definition of distance. So a distance is a real number, which is a function of two elements of a set, say x and y. And the three properties that define the distance are these ones. So the distance between x and y should be always larger or equal to 0, and it should be equal to 0 if and only if x is equal to y. The distance should be a symmetric function of x and y. Oops, I should change these arguments. See the final version in the web. It's almost a theorem. You may review your lecture, 10,000 times, and then at the moment you present it, you find something like that. And then you have the triangle inequality, which is this one. So question, okay, so that's a general definition of the distance. How can we define a distance between quantum states? Many of you think of the fidelity, we should define using the fidelity, but there is a problem with that. In fact, we know that two vectors of Hilbert space that differ by a constant, actually they're the same vector. Right? So the distance between them should be 0. So we would like to have a definition of distance that should be 0 between, say, psi and lambda psi. Now, a distance like that, there is a name for that. I warn you, I'm not a mathematician. I'm a physicist, so don't get scared. So this means that the distance will be defined in what we call a projective Hilbert space. Some of you may have heard of the space of rays instead of the space of states, and that's a projective Hilbert space. So a projective space in general is obtained from a vector space by identifying vectors that differ by a non-zero factor. Okay, so that's the definition. Now, also, in order to define a distance, one needs a metric, that is, something analog to the Riemannian metric in Euclidean space, something analog to that. Now, suppose d psi is an infinitesimal variation of some state psi, and that variation may come, for instance, because of the variation of some parameter, which the state psi depends on. That parameter might be time, for instance, if the state evolves. So we can write then that d psi is equal to this expression, is the derivative of psi with respect to x times dx. So one possibility would be to define the metric as just the norm of d psi. But this is a bad definition. Okay? And it's a bad definition because it would lead to a distance different from 0, say, between psi and this, and e to the ix psi. Remember, x is a parameter here. Or even this. And between this and this will give me a distance different from 0. And they correspond, in fact, to the same state. So how can we do that? Well, we can do something like that. See, before looking at this equation, just look at this expression. We have some change in psi, but then we subtract from this change the part that is collinear with psi, because we don't want to take that into account. So what's left is orthogonal to psi, and that's what is done here. D psi orthogonal is equal to d psi minus the projection of d psi on psi, which is given by this expression here. Now, note that if we define this displacement like that, then you see that if we multiply d psi here by some number, dz, times psi, then this will be equal to 0. Just replace this here, and you see that this whole thing vanishes. Okay? So very good. This is not sensitive to the multiplication of psi by some number. Now, we would like to have something more. We'd like this distance here to be invariant under this multiplication. Okay? So we define now what is called an angular distance or projective distance, which is just this divided by the norm of psi. So it's given by this expression here. And this measure, this is a measure of changes in projective space. Okay? Real changes. Huh? Okay, so that the states really get different. Now we take the norm of this angular distance, and this gives us a differential form of the distance, which is defined in this way. So this is called the Fubini study metric. Okay? It has some interesting properties. First, you can check it's invariant. It's trivial from here. It's invariant under any unitary U applied to both psi and psi plus d psi. Furthermore, it does not have the inconvenient features mentioned before, because it gives me zero distance between collinear states, and it does not. It's invariant under the multiplication of psi by some number. From this expression now, we can find a finite distance between two states in Hilbert space. Okay? So that's the distance we are going to use now for pure states. So we are now going to integrate this, and the idea is to integrate this along the shortest path, which is the geodesic in state space. Two vectors, and the distance you obtain by integrating this element of distance along the shortest path between these two vectors. Now, I'm not going to derive this for you. You can look at this thesis here, which is available in the web. It's in English. That's a student of Ruine Matos, a colleague of mine in our group. And what it can be shown is that this geodesic, this is actually intuitive, lies entirely in a two-dimensional subspace of the vector space, which is spanned by initial and final states. Okay? So we have these two states here. The geodesic lies in this plane, which, when I say it's intuitive, is that because if you go out of this plane, you should increase the length of this path. You are looking for the geodesic. And in fact, a motivation for that, if you want, is the analogy with a unit sphere, for which the geodesics are the great circles. And therefore, you have two states. The geodesics are segments of great circles, which, of course, include the origin of the Bloch sphere. And therefore, the geodesics is contained in a plane defined by the two vectors. Okay, so that's the idea. Now, this also implies that the geodesic can be expressed as a parametrized superposition of the initial and final state, because it's a plane. Okay? We can even have a Bloch sphere picture of that, because it's a two-dimensional space. Now, so what we do now is the following, and this is described in this thesis, the calculation. So we consider that psi 0 and psi f are the initial and final states. We get some state psi 1, which is orthogonal to psi 0, so now we have a basis, orthogonal basis in that two-dimensional state. And we write the state along the geodesic as a superposition of psi 0 and psi 1, okay, with functions f of s and g of s to be determined. These are complex functions of x. Now we turn the crank. Okay? We take this expression, we replace into this expression for ds squared, and we integrate and find the path that minimizes the length. We now have two functions, and we have to look for the functions f of s and g of s that minimize the length. And then by doing that, we find the finite distance between psi 0 and psi f. So that's the general idea. If you want to look at the calculations, they are not very involved, but you have to calculate this, do this minimization. So if you do that, you find an interesting expression. You find that the distance, according to the Fubini study metric, between the initial state and the final state is given by this expression here. Is r cosine of this. You see that, perhaps this is too detailed, but I'm actually dividing by the norm since I'm considering this projective space. So just I'm careful about that. Also, from this you see that the maximum value of this distance is when the r cosine is equal to pi over 2. It's between 0 and pi, the definition. So, okay. So, and this corresponds to orthogonal states, r cosine 0. Okay. So this is the normalization, if you want, of the Fubini study metric. It's not intuitive for those who like a Bloch sphere because, this is orthogonal to that and it looks like pi is the angular distance, but, that's the normalization used here. Now, this argument of the cosine is actually the square root of the fidelity. The fidelity is just the square of psi 0, psi f, if they are normalized. So we can also write this as this expression here. So you see that the distance, if you're considering distance between pure states, is a function of the fidelity between them. Not surprising, but it's this function here, the r cosine. Now, on a Bloch sphere, this would actually correspond to the shortest path along a great circle connecting two vectors with tips on this sphere. Now, so with these geometrical notions, now one is able to derive the Mandelstam term, I'm going to show you soon, based on geometrical arguments in a very simple way. But before doing that, I'm going to compare this distance with another one, which is perhaps better known, but does not serve our purposes. And this distance was also defined by Bures. It's given by this expression here. This is again the fidelity. And in order to understand the motivation for these definitions, just think about vector spaces. You have here two unit vectors, A and B, and I want to calculate the distance between them. This is orthogonal to this distance here. So this is θ over 2, this is θ over 2. And this distance, of course, is twice the projection of this vector onto this direction here. So it's equal to 2 times sine of θ over 2. But sine of θ over 2 can be written as 1 square root of 1 minus cosine of θ over 2. So this can be written like that. And cosine of θ is just the scalar product of A and B. So this corresponds precisely to this. Okay? So this is the distance defined by Bures also. But you see, here you can already see the problem. This path here is not along the Bloch sphere. It's interior to the Bloch sphere. And we are dealing here with pure states. Okay? So the path does not belong to the space we are dealing with. And in fact, the Fubini's study metric corresponds to this dashed line here. Okay? So it's a path along the space of states, while this distance, which I have just introduced, corresponds to this path here, which includes non-normalized states, necessarily. Okay? So this actually distinguishes state according to their norm. So it's not a path in projective space. Okay? Also, of course, it cannot be obtained from the Fubini study metric because this is independent of normalization. And here you have to deal necessarily with unnormalized states. Okay? So we are going to use this metric here because we want to talk about geodesics in state space. Okay? Now let's go for the geometric derivation of the Mandelstam term bound. In order to do that, we consider now that the parameter x is time. Okay? So if that is true, then this variation of psi here is given by this expression here. And this we can write immediately by using Schrödinger's equation. It's the Hamiltonian applied to psi times dt. So the parameter is now time. Now I introduce this deep psi into the expression for the Fubini study metric. And this gives me this expression here. And you see here that you get the variance of the Hamiltonian. So this is the variance of the energy in this state, times dt squared. Now I integrate both sides along the path followed by the state. So integrating this differential here, I get the length of the path. And on the right-hand side, I just have this integration here. I integrate this expression. Now, you see, this is the length of the path actually followed by the system in view of the dynamics dictated by the Hamiltonian H. Okay? It's not the geodesics, because there is a Hamiltonian there that leads the system. Now, the Mandelstam term bound corresponds simply to writing that the length of this path should be larger or equal than the length of the geodesic connecting the two states. Okay? That's the Mandelstam-Tam relation. Okay? So it's actually a geometric relation in the space of quantum states. Now, let's elaborate a little bit more on this relation. I repeat it here. So it can be interpreted in the following way. You see, on this side here, on the right-hand side, you have some integration. So if you plot delta E t over h bar as a function of t, this integration corresponds to the area under this curve here. And you might be interested in the following question. I want to find the bound on time for a certain distance d1 to be reached, okay, between the two states. Or I may say for some fidelity to be reached. In order to do that, okay, you have to integrate this, and this bound of time is given by the value, say t equal to tau, such that the area under the graph equals the distance you want to have. Okay? So that's the geometric meaning of this relation. So this is actually a lower bound on the time. Now, this leads us also to a geometric interpretation of the quantum Fisher information. Again, I repeat this expression. See, by the end of the lecture, you'll know by heart this expression. So this is the Fubini study differential. Now, suppose that the change in psi is due to the change in a single parameter x. Then, again, we have d psi equal to derivative of psi with respect to x time dx. And therefore, for a normalized psi, I can forget about these factors in the denominator. I have that the Fubini study metric is given by this expression here. It comes directly from that. It's just the derivative times dx squared. Now, if we compare this with the expression for the quantum Fisher information derived in the second lecture, which I presented in the introduction to this lecture, you see that the quantum Fisher information is just 4 times this. This term here, which is multiplying the x squared. Therefore, we can write that the Fubini study metric is 1/4 of the quantum Fisher information times the x squared. Okay? So you see that the quantum Fisher information is directly related to the distance between nearby states. And in fact, that shows that, you know, the larger the quantum Fisher information, the better will be the precision on the estimation of x. Because for the same dx, the larger will be the difference between the initial and final state, the more distinguishable will be the states. So that takes us to our second lecture, in which I mentioned that quantum metrology has to do with the distinguishability between states, quantum states. And you see that indeed the quantum Fisher information is directly related to that. Okay? So all of this is for pure states. What about mixed states? So I'm going to derive here in the next 2 slides this expression here, which is a generalization due to Bures of the Fubini study metric. What Bures showed is that the distance between 2 density matrix, ρ1 and ρ2, can be written by this, is also an arc cosine of the square root of some fidelity, but the fidelity now is defined in this way here. Okay? Homework assignment, show that it is symmetric between ρ1 and ρ2. Item A. Item B, show that if you have pure states, this reduces to that, which is the fidelity for pure states. Okay? So that's the expression due to Bures. Now, you can verify that this satisfies all the desired properties of a fidelity, but furthermore, there is a theorem by Bures that actually motivates this expression. What Bures showed is that the Bures fidelity is given, can be expressed in terms of purifications of ρ1 and ρ2, the famous purifications coming again. And what he actually showed is that this fidelity is the maximum value of the scalar product between 2 purifications, when you look for the maximum of this scalar product over all possible purifications of one of the density matrices. You just have to look for the maximization of one of the purifications. You don't have to care about both of them. Okay? So that was shown by Ullmann. And that's, of course, the fidelity for pure states. So that's a nice definition of fidelity between mixed states. You just look for the purification, and you look for the maximum value of this scalar product, and you define that as the fidelity between two density matrices. Now, so this sort of motivates the definition of Buur's fidelity. We are going to give now another motivation, which is related to the derivation of this expression here. So the idea is the following. First, we use the definition, again Buur's, given by Buur's, of the differential form of the distance between two neighboring states, rho and rho plus d rho, okay? Two close by density matrices. And the definition given by Buur's is that, again, this is the minimum distance between the purifications corresponding to rho and rho plus d rho, minimum over all possible purifications. Okay? So that defines the distance between the two density matrices. Again, the same idea as before. You look for the purifications, you look for the distance between these purifications, and you look for the minimum of the distance of all possible purifications, and you define that as the distance between two density matrices. Now, the corresponding length, then, is given by the integration of this over some path. Now, again, remember that this is given by the minimum of the Fubini-Study metric over all possible purifications. And this should be done for all purifications of each state in the path. Okay? And this can be written, the minimum we can take out of the integration if you understand that the minimum is given by that. And so this is the minimum of this path over all possible purifications along the path. I find it funny that something which seems so complex as this gives us at the end a very simple expression. Now, this distance between rho 1 and rho 2 is now defined as the length of the shortest path between the states, which means what? It's just that. It's the minimum of all possible, it's the minimum of LB, say. Okay, so first you construct some path, and then you take the geodesic, but it's a complex geodesic, right? Because you have to do it, it's a geodesic over the purifications, you have to take the minimum over all states, and you take the minimum path. And I let you to, I'll leave to you to think a little bit about this. So this is the minimum path of the minimum of LFS, which is LB, and the order of this can be interchanged because it has two minima, and you can interchange them. So I repeat this in the next slide. So now I have the distance between rho 1 and rho 2 is the minimum over all purifications of the minimum path between these purified states. Now, the minimum path over this purified state is actually geodesic in this extended space, and that's by definition the Fubini-Study metric. So this is the minimum over all purifications of the distance between these two purifications. And now I can use the expression we had before for pure states. The Fubini-Study distance is given by this R cosine. We have seen that before. So now we need the minimum over all purifications of this R cosine. However, the R cosine is a decreasing function of the fidelity. As the fidelity increases, the R cosine is reduced. And therefore, this minimum, finding this minimum, is equivalent to calculating the R cosine of the maximum of this fidelity over all possible purifications. But we saw before Ullmann's results that this maximum is precisely equal to the Buur's fidelity. Okay? So that shows that indeed the distance between two density matrices is given by this expression, where this is the Buur's fidelity. Okay? So now an exercise in calculus. let rho 1 be equal to rho of x, rho 2 be equal to rho of x plus dx, where x is a parameter. And let's now expand d of b as a function of dx. Okay, so first we expand the fidelity as a function of dx. There will be some derivatives, and you get this. And then you find that the quantum Fisher information shows up here. And now you plug this into that. You may use this expression, and you finally find that the distance between two density matrices is proportional to the square root of the quantum Fisher information times dx. So this is a very important expression because it shows that 1/2 multiplied by the square root of the quantum Fisher information is the speed of change of the distance between the two states. I call it speed in a general way, in a general sense. If x was the time, it would be the real speed. But for any parameter, it's the speed of evolution if the parameter changes. Okay? So that's a very important concept, and that's going to allow us the generalization of the Mandelstam term for open systems. There are calculations in this paper here, but I'll give you a derivation without any calculation, just using the concepts we had before. You see, we now are replacing the Mandelstam relation by this expression here. And let us understand what this means. This, as we saw before, is the Beer's length of the geodesic between the initial state and the final state. While this term here is the Beer's length of the actual path followed by the state of the system. Remember, this is the speed. Times dt integrated over 0 from 0 to tau gives me the path followed by the system according to the dynamics which is embedded into the quantum Fisher information, which is a function of time. So this is just saying that the Beer's length of the actual path followed by the state should be larger or equal than the length of the geodesic connecting the two states. Now, of course, here we don't have the energy because it's an open system in general. So we have the quantum Fisher information. In fact, this expression, as before, gives us the lower bound for the time needed to reach fidelity, say, given by the phi b, between initial and final states, or some distance between them. Now, in order to see how this relates to the previous expressions, let us consider a special case. So we consider now some unitary evolution, just the simplest possible case, time independent Hamiltonian, and suppose the final state is orthogonal to the initial one. Now, if we do that, then you see the fidelity between the initial and the final state is 0 because they are orthogonal. So this is going to be 0. A cosine 0 is pi over 2. So this side will give me pi over 2. What about the right-hand side? Now we have some unitary evolution, and it's a time-independent Hamiltonian. We know that the quantum Fisher information is 4 times the variance of the Hamiltonian, in this case, over h bar square. So we replace this here. We take the square root. The integration with respect to time here corresponds just to a multiplication by tau, because this is independent of time. So we just get this expression here. And this is precisely equal to the Mandelstam-Tam relation, okay? Which is just a special case of this general expression here, okay? So we may be happy from the conceptual point of view that we now have an extension of the Mandelstam-Tam relation, but there are some problems in actually calculating this. And maybe you should be familiar with these problems. We now have to calculate the quantum Fisher information for an open system. And in general, that's not easy at all. But we have that method. We can extend the space and find an upper bound for the quantum Fisher information. So that's the idea here. We go to a purification, and we write down now that the distance between the two states is bounded above not just by that, but also by this quantum Fisher information of the whole thing, which is an upper bound for that. So we can write that this distance is smaller or equal than this expression here. But this expression now corresponds to the extended space, unitary evolution, so I can calculate it explicitly. It's given just by the average of the variance of the generator of this evolution in the extended space. And the expression is this one. And of course, this H is just the generator as before. And this is the evolution of the purified state corresponding to rho s. Now, so that's a way of getting an upper bound for this. And therefore, if we find an upper bound for this integrand, that means a lower bound for the time. Now, let me give some examples so that you see how that works. And in fact, when we started to work on that, we are quite surprised actually about this example. After you see it, you are not surprised at all. But it's an example which shows us that our method is exact in this case. And then I'm going to show you another example for which the method also gives us exact results. So, in lecture 3, I mentioned to you the amplitude damping channel. And it may be described by these following equations here. You can think of the system as a two-level atom. I'm writing the index E for the environment, but I'm not writing the index S for the system because I find that that's very well determined here, okay? So I'm trying to simplify the notation. Now, so 0 and 1, you can think about the ground state and the excited state of a two-level atom interacting with the continuum of the electromagnetic field, if you want. So if the atom is in the ground state and the field is initially in the vacuum state, they both remain there. If the atom is in the excited state and the field is initially in the ground state, there is some probability that the system remains in the initial state and some transition probability to some state in which the atom goes to the ground state and the field acquires one excitation, or the environment acquires some excitation. Okay? Now we write P of t as an exponential of minus gamma t. I mentioned before that this actually corresponds to the Weiskopf-Wigner treatment of the decay of a two-level atom. So this is the map. And you see that from our point of view, this is a quite natural, physically motivated purification of the evolution of the level atom. Right? So that's the usual equation one writes if one wants to deal with this evolution as a unitary evolution. So we have to include the environment. The unitary evolution corresponding to this map is this one. You can check that later, where these operators here, just Pauli operators that do this. If you apply sigma plus to the ground state of the atom, it takes you to the excited state. If you apply sigma minus to the excited state of the two-level atom, it takes you to the ground state. These two operators satisfy this relation, which means that if you apply twice this operator, it gives you 0. Also, sigma plus, sigma minus is just a projector onto the excited state. Now, so this is the evolution operator. Now, if we have the evolution operator, we can find the generator as before. And you can therefore find this quantum Fisher information for the whole thing, which is related to the variance of the generator of this transformation here. So by calculating this, we get then this expression here. The distance should be smaller or equal than this expression that depends on time. Now, this quantity here is just the initial, not the whole thing, but this quantity here is just the initial population of the excited state. So it depends on the initial population of the excited state, since this is the projector on the excited state. Okay? Now, so I repeat this expression here, and now you see I can invert this expression by expressing time with respect to d. So we then get this relation. So you see that indeed we get a lower bound here for the time corresponding to some distance between the two states, the initial state and the decaying state. Again, this is the initial population of the excited state. So this is just a bound. And in principle, we cannot assure that this bound is tight. Okay? However, we can show that it can actually be saturated. There is a trivial example. Take this quantity to be equal to 0. That means that you are in the ground state, right? Since this is the population of the excited state. Now, if this is 0, then this should be smaller or equal to 0, which means that d is equal to 0. So the distance is 0. The state does not evolve. It's the ground state. Another less trivial example is when this state, the atom is initially in the excited state. Then, in this case, this initial projector here evolves into this superposition. This is just a mixture of the excited state and the ground state. And it's easy to calculate the fidelity between this state and the initial state. The fidelity should be equal to the scalar product between them, so it's given by the square root of this probability. And if you have the fidelity, then you can calculate the distance. It's r cosine of the fidelity, so the distance is given by that. And you see that that's just equal to this expression with the equal sign, since this is equal to 1. Okay? So you see that this evolution here saturates this expression, so you have a very good bound. It is a tight bound. Now, interpretation of this bound, you see, if the initial state is an excited state, then you have the amplitude damping channel, the evolution is along a geodesic. So the evolution is like this. And because it is along a geodesic, you saturate this expression. Okay? Also, you can use this expression for several aims. For instance, you can calculate the time for getting to the origin. At the origin, you have the identity here. So if that means that the fidelity is equal to 1/2, fidelity with respect to the initial state. The distance is equal to pi/3, so you get this expression for gamma tau, okay, for reaching the origin. You can also ask for the time for getting the excited. That should not be very surprising to you. Getting the excited, that means that the distance, initial state is excited, so this is equal to 1. So the distance should be equal to the maximum possible distance, which is pi/2. And in order for that to be equal to pi/2, time should be equal to infinity, which is obvious. Okay? Time should be infinite to get this completely excited. Now, you should also remark that there is some important difference between this metric here and the Euclidean geometry on the Bloch sphere. We saw that, which I have just mentioned, that this axis here is a geodesic for the time evolution of the system. But these are also geodesics for that on the Bloch sphere. In other words, if you use this metric here, you can find several geodesics, say between the North Pole and the South Pole. Of course, along the surface of the sphere is obvious. But furthermore, you can show that the length of this line here is equal to the length of this curve on the surface. You have to calculate it to believe. Okay? So if you use the Fubini study method, there are several geodesics, and that's why this decay, we can consider that the decay, not the Fubini study, I mean generalization to mixed states, sorry. There are several possible paths, geodesic paths, and this is why this trajectory here saturated the relation between distance and time. Which is, by the way, a way to show that that's also geodesic. Okay? Now, another example, the dephasing channel. The dephasing channel may also be defined by a map and by the following set of equations here. So if you look at these equations, you find that first the states 0 and 1 factorize here. So they are not affected by this channel. On the other hand, if you start with a superposition like 0 plus e to the I phi 1 over square root of 2, say, it's simple to notice that as t goes to infinity, that goes to 1, p of t. And therefore, you get here superposition with equal weights. T going to infinity, that p of t goes to 1/2. So you get here superposition with equal weights. And therefore, 0 and this superposition here gets entangled with two orthogonal states of the environment. So we get a state like that. This is a maximally entangled state, which means that you have lost completely the phase information in the system. On the other hand, of course, if you can do joint measurements of system plus environment, recover the phase information. And that should be a sign for us that, maybe this purification that we have here is not the best one. because after all, measurements on system plus environment do give us more information than measurements on the system alone. So this is a possible purification, but we can do better than that. And first, remark that the unitary evolution corresponding to the map can be written like that. Again, these are Pauli matrices for system S without the index, and these are Pauli matrices for the system, for the environment. So this is again the expressions I had before. So this is a possible purification of the evolution. Now, let's look for a more general unitary evolution along the way I showed you in the beginning of this lecture. So we should look for a unitary evolution on the environment itself. And we should minimize the quantum Fisher deformation for the whole thing over all possible evolutions, U sub E. And we know that this quantum Fisher deformation for the whole thing depends only on the generator of this evolution U of E, which is given by this expression. Now, this is a nice example, because we can actually write down the most general transformation we can do. After all, we are dealing with a simple spin. And so the environment is like a simple spin, because only two states of the environment are populated, the 0 and 1. So the most general Hamiltonian we can write down, most general generator of this evolution, is a combination of Pauli matrices. The identity does not play a role, because it's just a general phase. Okay? So now we have coefficients, which we are going to consider as variational parameters, and we can deal with them so as to minimize C of Q. And of course, it's clear that if we do that, we are going to get a tight bound, because that's the most general transformation we can do. So let me give you an example of the solution. The solution is actually, in general case, complicated, but I'm going to show it to you in a simple case, the case in which the two atomic levels have the same energy. And the superposition is submitted to some dephasing. Now, then we can show that this distance between the initial and the final states is bounded above by this expression here, where this is the variance of the Pauli operator sigma z. And I'm representing here sigma z by z just for economy of notation. Okay? So, first remark, if the variance of sigma z is equal to 0, that means that we have an eigenstate of z. So this is equal to 0, and this should be equal to 0, no evolution. It's clear from the equations I showed you before. If the states are 0 or 1, they do not evolve. Okay? On the other hand, if you have the maximum possible value of this variance, which is equal to 1, we can show that this bulb is saturated in the same way I showed you before. So this will be equal to 1. You can actually calculate explicitly the distance and show that the distance is given by this expression with an equal sign. Okay, so you saturate the bound. Now, what does it mean that? What's the interpretation of that? Well, if you have pure states with maximum variance, that means that they are here on the equatorial plane. Now, remember that omega 0 is equal to 0. So the evolution of these states is along a geodesic of the Bloch sphere. They are going towards the center. So 0 plus 1 over square root of 2 at time infinity becomes just the identity in this space. So this is the evolution. And because the evolution is along a geodesic, you should saturate the bound. So that's the idea, as usual. Okay. Now, we have also applied this to a collection of spins. I'm going to jump over this slide. It is in the slides I gave to you, because I don't want to overcharge you with too many examples. And I want to go to another example of application of these considerations, which may be more interesting than just considering a collection of spins for the moment. So as a final two slides of this presentation, I'm going to show you how these concepts can be applied to quantum control. And I'm going to give you a very simple example, which was discussed in this paper here. The idea is the following. We start with the ground state of some Hamiltonian, and we have as target the ground state of a modified Hamiltonian as in adiabatic quantum computation. So you start with some ground state of a Hamiltonian should be simple enough so that you can solve it. And then you turn on the interaction slowly. So this ground state should go to the ground state of the complete Hamiltonian, and then you get it just by turning on the knob slowly enough. Now, what they do is actually a numerical approach, and they consider this example here, which is called the Landau-Zener Hamiltonian, is a spin interacting, say, with a time-dependent magnetic field along the z direction, and also with some other magnetic field along the x direction. These are the energy levels for this Hamiltonian as a function of gamma. What they consider as the problem is to start with the initial state of this Hamiltonian in initial time when gamma is equal to minus gamma 0, so it's negative here. And the target state is the ground state of the Hamiltonian with gamma equal to gamma 0, that is gamma here. Okay? And they want to go from here to here. And of course, if they don't go slowly enough, you might jump to this state here. If they go adiabatically, then you go like that. What they want to show is that there are ways of doing this which take you to the final state with sufficient fidelity and which are faster than the adiabatic way. Okay? So what they show by using this algorithm here, it's a numerical algorithm, is that the best way is to have a fast change in the beginning and the end, and basically to set gamma equal to 0 in between. So gamma is a control parameter. Okay? Now, we wanted to understand this analytically, and in fact, this can be understood, in this case, by using the concepts we developed before. So this is the Landau-Zener Hamiltonian. You see, this is like a pseudo-magnetic field interacting with some spin. So the spin should precess around this pseudo-magnetic field. So that's the precession equation for the spin. Now, we know now that we are dealing with pure states here, that r cosine of the square root of the fidelity between the initial and final state should be bounded above by this expression. Of course, E is a function of t because of this gamma here. And we just write for simplicity that that should be bounded below by the maximum value of this variance times tau. Okay? Just an upper bound to this integral. Now, of course, if you have a path along the Bloch sphere, then this variance can be very large if gamma is unbounded. Okay? Because it will be a superposition of the up state and the down state, and that would be very large. Indeed, if gamma is unbounded, delta E could be very large, and if you take tau from this relation, you see that tau is bounded below by this expression, and since delta E max goes to infinity, this expression goes to 0, which means that you have a curious bound. Looks like useless. The bound tells us that the time is larger or equal than 0. Yeah. However, this is a tight bound. Let me show you why. Consider this evolution here. You start with a state here, and of course, the magnetic field along Z is very, very high. So this state will evolve in this way, and the evolution is as fast as you want. So the evolution time indeed goes to 0. As gamma goes to infinity. That's what's the meaning of this bound. Some people have said that this bound is wrong because it's not wrong. It's a tight bound, but it's it's nice to see it's bound. It's tight, but if you just look at that, it's deceiving. However, the concept of geodesy can be very useful to understand this problem. Suppose now we have some general initial state. I'm not even mentioning the ground state of that Hamiltonian, general state. On the Bloch sphere, and we want to go to another state on the Bloch sphere, but we have an unbound gamma t, unbounded. So question, how can we do it? What's the best way to do it? Well, this plot shows the idea. we should try to reach a geodesic as fast as possible, but profiting from the fact that rotations around Z can be as fast as possible. So that's the solution. You start here. That graph plot was done by Bruno Escher, and he could not resist the temptation of putting flags, of initial and final flag, like a car race. So you start here. So here you have a fast rotation around the z-axis that takes you to the geodesic, this big circle here. And then you go back to the final state, also as fast as you want. Now you see, this corresponds precisely to going as fast as possible in the beginning, setting gamma equal to 0 at the end, and then going as fast as possible to the final stage. So that's the geometric interpretation of going fast first, then gamma equal to 0, then going fast at the end. Okay? So, and this, of course, agrees with the results by Caneva and all in the paper I showed you. Now, conclusions of the series of lectures. So, my aim was to give you an introduction to quantum metrology. There are lots of things in this field that I have not talked about, like, for instance, estimation of several parameters, which means that we are going to deal with a quantum Fisher matrix. The problem of open systems has had many papers on it since this paper showing the expanded space was published. There are other methods available in the literature to find some approximate solutions of this problem. Of course, we like this method just because we are used to it, and we have had some success with it, but there are other methods which are good enough, and have been presented in the literature. Now, we have exemplified this approach with examples regarding, for instance, the estimation of a weak force acting on a damped harmonic oscillator, or the estimation of phase in a noisy optical interferometer, which could have photon losses or diffusion of phase. And we have also shown that this approach can lead us to a generalization or to an extension of the Mandelstam-Tam relation to open systems. And we have exemplified that with typical examples of open systems. I have not shown you the many spin case, but you can see in the notes, we also get some very nice results doing this kind of variational approach in which you start with some extended Hamiltonian, and then you try to minimize the corresponding quantum Fisher information. And of course, we had a spectacular application of quantum metrology during this course, which was the detection of gravitational waves, where the ideas that I presented in the first lecture were used. Remember, I showed that you can combine a coherent state with a squeezed state in order to get a better precision. And indeed, in this detection, they used the squeezed states. That was the proposal by Caves. And that's an example of the challenges of quantum metrology nowadays. Okay? In the paper, it's not mentioned. It's not. But I heard that they are using it. But they did not use the experiments. I see. Because I heard from someone that they had used, someone that had some contact with the experiment. But okay. Anyway, but we will get there. We'll get there. Because indeed, with squeezed state, you get a better precision. Okay, even better than what they were obtaining in principle. So I don't want to finish without mentioning the collaborators in this team. These are former students in our group. Gabriel Bier had his thesis on the weak value amplification problem, Márcio Tadei on the quantum speed limit, Camille Latoun on the estimation of weak forces, and Bruno Escher his thesis was on the method. It was really on the idea of extending the space, and he had a very important participation in that. These are my colleagues in the group, Nissim Zaguri and Ruiné Matos Filho. Márcio Tadei was a student of Ruiné Matos Filho. Gabriel Bier, Camille Latoun, and Bruno Escher were my students. And Bruno Escher is now a professor in our group. So he should go with the others. Now, thank you very much for your attention and patience, and I'm waiting for questions.